Good morning, guys. Now, in previous lecture, actually we have derived the one-dimensional. We have derived the derivation for stiffness matrix, means elemental stiffness matrix for one-dimensional spring element. In the previous lecture, actually we derived the stiffness matrix for one-dimensional bar element. Then we have taken the relation with that bar element and we derive our one-dimensional stiffness matrix for spring element. Okay, so and in previous lecture I have given you one homework to construct a global stiffness matrix for the given example. So given example is what? There are three springs system is there. For first spring constant K1 is given as 100 kN per meter. For second K2 is given as 70 kN per meter, and for third spring the stiffness K3 is given as 700 kN per meter. Okay, and the question was that find out the elemental stiffness matrices, and then next is construct the global stiffness matrix. Okay, so we will solve this example. So first find out the elemental stiffness matrices for each element. Okay, so actually as there are three elements, okay, this is first element, this is your second element, and this is your third element. Okay, so there will be four nodes because number of nodes is equal to number of elements plus 1. This is the standard equation to find out the number of nodes. So number of nodes is equal to number of elements plus 1. As there are three elements, there are three spring elements plus 1. So N will become, so the number of nodes for this spring system should be equal to 4. And from this node we will define our order of the global stiffness matrix. So order of global stiffness matrix will become of 4 by 4. So it should be 4 by 4 because there are 4 number of nodes. Then the order of that matrix will become 4 by 4. Now we will see how we are going to construct this global stiffness matrix of order 4 by 4. Okay. So first find out the elemental stiffness matrix for each element. Okay. So first we have to denote the nodes for this spring system. So this is your first node, this is your second node, this is your third node, and this is your fourth. Okay. As there are three elements, there should be 4 nodes for this spring system. So now for each element we need to construct an elemental stiffness matrix first, and by using this elemental stiffness matrices we are going to construct our global stiffness matrix of order 4 by 4. Okay, so first for this first element we need to construct our elemental stiffness matrix E1. Okay, now as we know that the elemental stiffness matrix for one-dimensional spring element is given by formula K minus K minus K K. Okay. So by using this generalized elemental stiffness matrix for one-dimensional spring element, we are going to finalize our elemental stiffness matrix for these three elements, element 1, 2, and 3. Okay. So from this we will write down the elemental stiffness matrix E1 for first element as, instead of K, the value of K is given for the spring element 1 is equal to 100 kN per meter. So it will become 100 minus 100 minus 100 and 100. And actually the position of this element, it is in between node 1 and 2. So we need to write down the position of this element in matrix form also. So we can write it as, actually it is between position 1 and 2. Okay. Now next is what? Write down elemental stiffness matrix for second element. So in similar way, for first element we have written. So in similar way we can write the elemental stiffness matrix for this second element as E2. E2 is equal to, instead of K, write down 70 because the value of this K is given as 70 kN per meter. So you will get the second elemental stiffness matrix as 70 minus 70 minus 70 and 7. Okay. Then next step is write down the position of that elemental stiffness matrix between the given node. So this element 2 actually it lies between node 2 and 3. So write down this position of that elemental stiffness matrix or the elemental stiffness matrix. Okay. So actually this is position between 2 and 3. Okay. So in this way we can write the elemental stiffness matrix for second element. Now third and last one is elemental stiffness matrix K3 is given as the value of K3 is given as 700 kN per meter. So instead of this K, write down 700. You will get the elemental stiffness matrix 700 minus 700 minus 700 and 700. So in this way you will get the elemental stiffness matrix E3 for the third element. Okay. So next step is write down the position of that element in matrix form, as actually this element lies between node 3 and node 4. So its position will become between 3 and 4. Between 3 and 4. Okay. So this is the answer of your first question. Let's find out the elemental stiffness matrices for each element. As there are 3 elements, so we have to write down 3 elemental stiffness matrices E1, E2 and E3. Now next question is what? Construct global stiffness matrix. Okay. Now to construct global stiffness matrix we need elemental stiffness matrices, and first answer is here E1, E2 and E3. We have actually calculated. Now construct global stiffness matrix. How to construct global stiffness matrix? Actually, global stiffness matrix, the order of that global stiffness matrix K is nothing but 4 by 4. So we need to construct a 4 by 4 matrix between position 1, 2, 3 and 4. 1, 2, 3 and 4, and we will get the elements as K11, K12, K13, K14, K21, K23, K22, K23, K24, then K31, K32, K33, K34, and finally K41, K42, K43 and K4. Okay, so in this way you can write the elemental stiffness matrix. Okay, so now you are able to see this, our global stiffness matrix. Okay, as there are 4 nodes, so order of that global stiffness matrix will become 4 by 4. So this 4 by 4 matrix we can write in our generalized format as, in terms of elements, it will become K11, 12, 13, 14 up to K4. Now by using these 3 elements 1, 2 and 3, we will write down the global stiffness matrix. Simply what? Position these elemental matrices into your global stiffness matrix. Means what? The position of this elemental stiffness matrix is in between node 1 and 2. Means what? It is actually nothing but K11, K12, K21, K2. Okay. So similarly you can map this also. So it actually it is between 2 and 3. So it will become K23, K22 actually. This is second column, this is second row. So this element will become K22. This is your second row, third column. So this will become K23. Then finally, third row, second column. So it will become K32. Third row, third column. So it will become K33. Okay, then for this, actually its position is in between 3 and 4. So third row, third column, so it will become K33. Third row, fourth column, so it will become K34. Fourth row, third column, so it will become K43, and fourth row, fourth column, it will become K4. Okay, this is the one way of positioning these elemental stiffness matrices into global stiffness matrices. Second way is that by simply addition of these three matrices, you will get the global stiffness matrix of K 4x4 order. Okay, so for addition purpose, you have to write down this elemental stiffness matrix between order 1 to 4. So means you have to add this 3 and 4 of null values, 3 and 4 of null values. So it will become finally 0, 0, 0, 0. This will also become 0, 0, 0, 0, 0, 0, 0. So by practicing, you will come to know how to construct the global stiffness matrix by simply positioning of these elemental stiffness matrix into global stiffness matrix. Okay, this is one way. Second one way is what? Instead of writing this third and fourth column and rows of null values, position your elemental stiffness matrix as it is into your global stiffness matrix. Simply by putting the values of K11, K12, K11 and K12 into this matrix, K21 and K22, K21 and K22 into this matrix, you will get the global stiffness matrix by putting all these elemental values into the global stiffness matrix. This is the one way. Second one way is what? Actually we have gone through this second way. Means for each matrix, write down 4x4 matrix and write down this matrix into 4x4 format. Write down this matrix also into 4x4 format. Means 4 columns, 4 rows. Similarly, write down this third matrix into 4x4 format. Means write down 3 rows and 3 columns. Means remaining 2 rows and 2 columns will be of null values or 0 values. Similarly here, remaining 2 rows and 2 columns means remaining first row, first column as well as fourth row, fourth column. Similarly here, third row, fourth row as well as third column, fourth column of 0 values. Okay, so instead of doing this one, we will proceed it by positioning the elemental stiffness matrices into this global stiffness matrix. Now, how to position this elemental stiffness matrices into global stiffness matrices, we will see now. Okay, so I will write this E1 here. E1 is equal to 100 minus 100 minus 100, and this is between 1 and 2, this is between 1 and 2. So this element will become K11, this will become K12, this will become K21, this will become K22. Okay, so now write down the values. So finally, K global stiffness matrix will become equal to 1, 2, 3 and 4. Similarly here 1, 2, 3 and 4. Okay, so here position this E1. For this here only K11, K12, K21 and K values of K22 are known. So put these values into this matrix as K11, K12, K21, K22 means between 1 and 2. So means between 1 and 2 it will position itself. Okay. Second element, actually this element is in between node 2 and 3. So write down these elements into position 2 and 3. So between position 2 and 3, this is 2 and 3 rows, these are 2 and 3 columns. So it will position between these nodes, between 2 and 3 nodes. Okay. And finally, third one is between 3 and 4. This element is in between node 3 and 4. Means position these elements between 3 and 4. positions, means between third row, fourth row, third column, fourth column. Okay, so third row, fourth row, and third column, fourth column, third column, fourth column. So it will become like that. Okay, and remaining terms will become equal to 0. Remaining terms equal to 0. Okay, so this is nothing but a symmetric matrix. You will get symmetric matrix. So position. So as it is, write down this elementary stiffness matrix E1 into this block. Right? So 100. 1 minute. So 100 minus 100 minus 100 and here 100. Then similarly write down E2 or elements of this E2 into this block. So this will become here 100 already from first element, and now this 70 will come to this K2, this 2. So it will become plus 70 minus 70 and here 70. Similarly write down your third element into this block. So K33 means third row, third column. So it will become plus here, plus 700 minus 700 minus 700 and 700. Okay, so in this way we have written our first element 100 minus 100 minus 100 100 between 1 and 2. So between 1 and 2 means this block. So 100 minus 100 minus 100 100. Then second element 70 minus 70 minus 70 70. Second element actually it is between 2 and 3, means between second row, third row, second column, third column, means this is your column. So 70 minus 70 minus 70 70, and last one is in between node 3 and 4. So between node 3 and 4 means this block. So put these values into this block. So 700 minus 700 minus 700 700. Okay, so finally you will get your global stiffness matrix as this will be equal to global stiffness matrix K of order 4/2 will become finally 1 2 3. Okay, so this will become, first row will become 100 minus 100 0 0, 100 minus 100 0 0. Second row will become minus 100, this 100 plus 70 170, so minus 100, this 100 plus 70 170. Then third element is minus 70 and 0. Then third row will become 0 minus 70 0 minus 70 0 minus 70. Then 70 plus 700 700 70, and last one will become minus 700 minus 700, and final row will become 0 0 minus 700 700 0 0 minus 700 700. So this is your 0 0. Okay, so in this way you will get your final global stiffness matrix K. Okay, so in this way you can construct the global stiffness matrix for any spring system. Okay, this is your final global stiffness matrix K of 4/4 order. Now, if the spring system, we will take some another examples to construct the global stiffness matrix. So in this way you can construct your global stiffness matrix. So first step is to construct a global stiffness matrix. First step is you need to find out the elemental stiffness matrices first. So for this you need to find out the elemental stiffness matrix. E1, for this it is E2, for this it is E3. Then by putting these E1, E2 and E3 elements into the global stiffness matrix, by their positioning between position of the nodes, you will get the final global stiffness matrix K. Now we will take another example. Okay, so this is one example. We will take another example. Same example is there. Suppose 100 kilonewton per meter. Okay, only I will change the spring system as, here only I will change the spring system. Remaining values are same, kilonewton per meter. Only I will change here the spring system. Okay, this is the spring system. This first node, second node, third node and fourth node. So and the values of K for this spring system is equal to 70 kilonewton per meter. This is also 70 kilonewton per meter. This is also 70 kilonewton per meter. And if you are asked to find out the global stiffness matrix for this spring system shown in the figure. Okay, actually, and this spring system, it will shows like this is like the spring system looks like. Okay. And if you are asked to find out the global stiffness matrix for the spring system shown in the figure, for this K1 is equal to 100 kilonewton per meter. Then this is the parallel spring system, which includes 3 springs parallel to each other between node 2 and node 3 with spring constant K is equal to 70 kilonewton per meter for each spring, and third spring having spring constant is equal to 700 kilonewton per meter. Same example, previously there is only one spring. Now in this case the second spring is replaced by the parallel 3 spring system. Okay, so for this case, how to write the or how to construct the stiffness matrix? This is the question. Okay, so actually here there are how many nodes are there? Actually there are how many number of elements are there? 1, 2, 3, 4, 5 elements are there. But as shown in figure, here they have given the number of nodes already. 1, 2, 3 and 4. It means what? It means that this second spring system is considered to be a parallel spring system, and we need to convert this parallel spring system into one spring system. So this parallel spring system is converted into one spring system. If the springs are connected in parallel, then we will add the stiffnesses of each spring to get equivalent stiffness. So finally equivalent stiffness for this spring system will become, if the springs are connected in parallel, then we need to add the 3 spring constants to get the equivalent spring constant or stiffness of for that spring system. So the K2 will become 70 plus 70 plus 70. So K2 will become 210 kilonewton per meter. Okay. Now this system, it will looks like your 3 spring system. And actually we have derived or we have constructed global stiffness matrix for this spring system with K1 is equal to 100, K2 is now changed to 210, and K3 is equal to 7. Now same procedure is applied to construct the global stiffness matrix, and we will get the global stiffness matrix as here some changes are to be made. So first element, actually it is between node 1 and 2. So 100 value, there should be a 100 value between node 1 and 2. So 100 minus 100 minus 100, and this will become, initially there will be 100 value. Then second, this is between node 2 and node 3. Okay, so between node 2 and 3, the stiffness value is 210. So put the value of K2 is equal to 210 between node 2 and 3. Actually this is 1, 2, 3, 4. So between node 2 and 3, 2 and 3, 2 and 3 means this column. So it will become between 2 and 3, the spring constant is 210. So plus 210 minus 210 minus 210 and plus 210. Okay. Then for third spring constant 700, third element have spring constant is equal to 700 kilonewton per meter. So put this value of K3 between node 3 and node 4. So between node 3 and node 4, between node 3 and node 4 means this block. So instead of 700, now put this value of 700 into this block, you will get 210 plus 700 minus 700 minus 700 and 700. So finally you will get the global stiffness matrix as 100 plus 210, 310 minus 200, 200 plus 7, 910, 910. Okay, so these two values are changed as well as these values also changed. Okay, because initially there is only 70 kilonewton per meter, so it is changed to minus 200. It also changed to minus 200. So here 100 plus 210, it will become 310. And here 700 plus 210 will become 910. So this is the final global stiffness matrix for this spring system. Okay, so for such type of problems, you need to convert this parallel system of springs, this parallel spring system into an equivalent spring system. Then the same procedure by using the elementary stiffness matrix E1, E2 and E3. First you need to find out the elementary stiffness matrices, then you need to construct the global stiffness matrix by using this elementary stiffness matrices. First, so initial problem and this previous problem, actually we have constructed the global stiffness matrix from previous problem, but here change is what? Only the spring system is changed. Means initially there is only one spring, but instead of one spring there are 3 springs connected in parallel to each other. So we need to convert this parallel spring system into an equivalent one spring system. Then you have to follow the same procedure to find out the global stiffness matrix. Means first find out the elementary stiffness matrices, then find out the, by using these elementary stiffness matrices you are going to find out the global or global stiffness matrix K of order 4 by 4. So order, so first note down first thing. One thing is that the order of the global stiffness matrix is equal to how many number of nodes are there, and depending on that number of nodes your order will we become. Okay, if there are number of nodes equal to 4, then order of that matrix will become 4 by 4. If number of nodes are 3, then it will become 3 by 3. Okay, and how many number of elements are there? Depending on that number of elements, number of nodes also depend. Okay, so as there are one, this equivalence consisting this one and also this one, so there are 3 elements, so number of nodes will become 3 plus 1 4, so order will become 4 by 4. So this is about your construction of the global stiffness matrix. And now we will see how to solve this 4 by 4 matrix to get the displacement value as well as to get the strain and stress values in our next lecture. Okay, so we will conclude our lecture here only. So try to solve these examples at your own, at your home. Okay, so that will you get the confidence to construct a global stiffness matrix for the spring system, because same examples we are going to solve, but by applying the boundary conditions you are going to find out final results like displacement and stresses. But the same procedure is we are going to apply for every problem, so you need to have some confidence to construct the global stiffness matrix by positioning the elemental stiffness matrix over your global stiffness matrix. Okay, so here we will conclude our lecture.